So what I wanted to talk to you about today was a number of topics that my group and I and my collaborators have been interested in doing for a few years now. As Shai mentioned, I spend quite a lot of my time nowadays actually thinking about galaxy redshift surveys and the nature of dark energy. But for a long time, a lot of my research interest has been in the regime of the smaller scale structure in the universe and what it can tell us about the nature of dark matter. But today I wanted to pretty much fix the model of dark matter to one in particular, which is our old familiar friend called dark matter. And there's good reason for why this is a model worth considering. And this point need not be labored for too long. I think it's always a great testament to a model of structure formation where if you have some observations of the early universe, say in the form of the cosmic microwave background, you can write down a model for which you can compute the linear perturbations defined through 6 independent parameters, which give you a beautiful level of agreement with the fluctuations in the microwave background that we observed with CMB experiments. But that same model, which you can then forward, or sort of push forward to predicting structure formation in more recent times, also gives you a phenomenal level of agreement in the statistical distribution of galaxies on large scales. And this sort of connection has really been enabled by a sophistication and an improved level of calculations in terms of cosmological simulations. The example here being shown of the Millennium simulations, where you look at the distribution of galaxies predicted by the lambda CDM model in blue compared with the distribution of galaxies in the Sloan Digital Sky Survey. And at least visually, you find something that looks strikingly similar, which you can then obviously quantify and compare more robustly as well. For a long time, now we have established this idea that dark matter is the sort of unit of structure formation and the sort of sites where galaxies actually form. And we've developed this picture over several decades now that if we measure the mass distribution surrounding galaxies, either through different types of arguments of how the mass scales as a function of distance through things like timing arguments, or indeed by measuring things like the rotation curves of galaxies, it sort of points to this idea that the visible matter in our universe, the visible galactic matter or the baryonic matter, is sort of almost hugged by a halo of dark matter in the exterior. And this halo of dark matter is the thing that collapses first, within which the galaxies are forming. So dark matter halos seemingly are the sort of fundamental units along which structure formation proceeds. Now, exactly how full of dark matter halos the universe should be depends on the nature of the dark matter particle. And this is shown I think quite neatly in the form of this picture here, which is a power spectrum. So it basically measures, for want of a better phrase, the lumpiness of the universe as a function of scale, going from large scales to small scales. And different models of dark matter essentially predict different types of curves here. So if you think of completely cold, infinitely cold dark matter, you have a yellow line, which is underneath all of these curves and goes all the way over there. And it basically suggests that the amount of power that you have per wave number increases to small scales. And this is why it's the small scales that collapse first in hierarchical models of structure formation like cold dark matter. And in principle, this can happen, this collapse can continue indefinitely on all scales. If you have a slightly different model of dark matter where perhaps the particles are not infinitely cold, but they can have some kind of relativistic motions in the early universe, this induces a cutoff on the power spectrum on a particular scale, which is characteristic to the phenomenology of the dark matter. And what that means is that you can actually get a suppression of structures on some particular scale. So in the case of models like sterile neutrinos or warm dark matter, this scale is corresponding to the scale of dwarf galaxies. In the case of WIMP-like dark matter particles, this is many orders of magnitude smaller at Earth mass halos. So this is kind of the outline of my talk today. I want to focus on things that are essentially the smaller dark matter halos, not so much the Milky Way galaxy and clusters in this talk, but I want to focus on three regimes in particular. The first covers what I call the edge of galaxy formation, which are the smallest dark matter halos within which we think galaxies are actually forming. This is the regime of the so-called ultra-faint dwarf galaxies. I then want to move on to a mass scale a bit smaller than that, which is the smallest dark matter halos that we think that will ever hold a baryon or ever see a baryon in their lives, the so-called edge of visibility, visibility defined at least in terms of the presence of baryons in this case, and then get to everything else that forms below this scale, down to the very smallest halos, the Earth mass halos that we think exist in a WIMP-like or a cold dark matter-like universe, and what it tells us about the nature of structure formation itself. Okay, let's see how far I get through that. Right, so let's start with this regime here. So I said to you at the start, the cold dark matter model is really an interesting and a highly informative model that we've studied in great detail for a while. And one of the great successes of this is down to the fact that it is predictive in nature, that we can not only calculate the linear theory predictions of this model in terms of the CMB, but with the help of numerical simulations, we can make predictions for the nonlinear distribution of matter on extremely nonlinear scales. So this is a picture from the Aquarius project, which shows a high resolution simulation of the galactic halo. And one of the key predictions of the cold dark matter model is that a galaxy like the Milky Way should be surrounded by a very large population of substructures of dark matter that themselves could be the hosts of galaxies. And it's in this context that some potential issues with the cold dark matter model have sometimes been ascribed. Most prominently or most easily understood, perhaps, is the so-called missing satellites problem, which basically says that if you actually do a census of the tiny galaxies that we see that we see orbiting the Milky Way in the real universe, we get something that's of the order of 50 or 60 or so, which you can say, well, okay, we don't know what the full number is, so we can correct for the completeness of the survey and get a number that's maybe of the order of 100. But that's several thousand times smaller than the population of dark matter subhalos that these simulations seem to predict. And the question is, if this is such a great model, then why is this discrepancy present? So why do most of these subhalos remain dark? And I think this is understood pretty well these days, what the physics is and why this happens. And sort of visually, this is how you can sort of understand it. So imagine you have a picture which shows the growth of dark matter halos as a function of redshift, so their mass as a function of redshift. What you need is basically from a halo to be massive enough at some particular time that its gravitational potential well is able to trap hydrogen gas and cool it. So prior to the Epoch of Reionisation, this important phase transition in the early universe, this corresponds to temperatures or virial temperatures for halos that then can be mapped to a mass that is of the order of a few thousand Kelvin or so. This is the atomic hydrogen cooling limit. But then once reionization happens, this floor gets pushed up because the temperature of the gas is increased, and that critical mass scale shifts up by a factor of a few tens of thousands of Kelvin. Okay, so there's a mass scale before reionization and a mass scale after reionization. And so that's about 20,000 Kelvin or so. And in this simple model, if you have a dark matter halo that has a growth history that looks like this gray curve, such that it is always below this filtering scale, so it's always too low in mass to actually trap this gas, this is something that will remain a star-free halo, even at the final time. Whereas if you have one which ends up with the same final day mass, but has a slightly different history that allows it to cross these critical scales, this is something that will form stars. Okay, this is a very simple picture that has been known for a long time. In fact, some of this has been suggested long before the missing satellites problem was even posed. So it's in some ways a problem that had a solution before the problem was even stated, but nevertheless, this is the case. But what happens is that nowadays, in modern generations of simulations, even though the dark matter distribution around something like the local group looks like this, the distribution of the stars looks a little bit like that. Okay, most of these tiny subhalos remain dark because reionization essentially wipes us out. So this is a problem that me and several of my collaborators have been interested in for a while, to study what happens, what are the properties, what sets the properties of these really low mass, ultra faint galaxies surrounding the Milky Way. This is quite challenging to do statistically in a hydrodynamical simulation because of the extraordinary demands in terms of resolution that's required. So you can get a sort of intermediate solution from what is my favorite approach to galaxy formation. It's called semi-analytic galaxy formation, in which you basically say that you start with an n-body simulation that gives you the growth histories of dark matter halos. And then once you have that, you can put in models for gas cooling and star formation and feedback and so on. And what you get at the end is a prediction for the properties of galaxies. They look nothing like this, but you get a series of numbers that tell you what the properties of the galaxies are. But importantly, these semi-analytic models allow us to statistically probe a regime of these ultra-faint satellites of the Milky Way, so things that have stellar masses below 10 to the 5, statistically in a way that hydro simulations currently are unable to do. So a couple of years ago, we looked at this particular problem of, how do these satellites around the Milky Way grow in the context of these reionization-driven models? And you come to a picture that looks something like this. So here on the x-axis is the present-day stellar mass of the galaxy, and the y-axis shows what fraction of the mass of this galaxy was accumulated prior to redshift 6. If you just focus on the blue curve is a model in which reionization happens at redshift 6. And you basically see that there's kind of two regimes that's carved out here. One is the regime of the sort of fainter satellites, so things sort of to the left in this diagram, which are primarily accumulating the bulk of their stellar mass prior to redshift 6, so it's kind of frozen in at some early time. And the more massive galaxies, so things like the LMC and the Milky Way itself, I suppose, which have almost done nothing prior to reionization, and the bulk of it is happening afterwards. So there's a sort of two-stage formation channel for the Milky Way satellites. And this is not just a hallucination of this model. This is in fact something we actually observe when we try and infer the star formation histories of satellites in and around the Milky Way. And a lot of the star formation histories that we've measured for things that have resolved populations do seem to be consistent with the idea that a large amount of their stars has already been set in place by some very early time. So what happens when we try and actually predict the abundance of these galaxies now as a function of their luminosity? This is something called the luminosity function. So this is number of objects as a function of their brightness or their stellar mass. And the gray symbols are now measurements of the total luminosity function of satellites around the Milky Way, which has now been corrected for all of these survey incompleteness effects and so on. So you get something of the order of 120-ish objects or so. And now let's overlay the semi-analytic model of galaxy formation that I was showing you earlier, and it looks a bit like that, okay? This is this two-phase galaxy formation idea. And what I should stress here is that this regime of the ultrafaints has not at all been used to calibrate the properties of this galaxy formation model. It's solely based on the properties of much more brighter, much larger galaxies. But that same model with this idea of reionization, halting the star formation in these satellites, seems to give you something that looks reasonable. So you can run basically a bunch of experiments where you vary around some of the parameters of reionization, such as when reionization happens or where exactly this increase in the filtering scale kicks in, at what mass scale it kicks in. And you can develop a fairly general picture of what shapes the luminosity function of Milky Way satellites. And essentially, it's this idea of a sort of bimodality in this distribution such that if you change the redshift of reionization by making it earlier or later, what it really affects is primarily the abundance of the ultra-faint galaxies, because you're giving them less time or more time during which to form stars. Whereas exactly where this transition between the pre-reionization and post-reionization population comes in is set by the idea of this filtering scale, i.e., what are the typical masses of halos that are affected by the increased heating of the intergalactic gas. And these are both quantities that are, well, maybe this is slightly better understood, but certainly this is a parameter that is, not fundamentally understood from first principles, and it's debated.
Wait, I'm so sorry. Why?
Yeah.
Are the axes meant to be the same?
The axes, yes. It's just showing, so it's the gray curve is like a standard model, and it's just changing two parameters around and just showing how the shape responds to those. So it's number of objects as a function of brightness and how that's changing. Yeah. Another complication is added by the fact that it's not just the physics of reionization that changes the abundance of your ultra-faint galaxies or the low mass galaxies, but actually the history of the growth of the main halo, the host, the Milky Way itself, actually has differences in how many of these ultra-faints are actually found in there. So this is a picture which now again shows the luminosity function of satellites, so the number of satellites as a function of their stellar mass for things that have the same host Milky Way mass at the end, but they differ by how early this Milky Way mass object is actually assembling, whether it's an early forming Milky Way or a late forming Milky Way. And the histograms basically split that. And what these models seem to predict is that the difference in the assembly time of our host, which hopefully we are able to constrain better now with things like I and so on, actually has a non-negligible effect on the abundance of these ultra-faints. So why does all of this matter? I think this matters because the abundance of these kinds of galaxies is often used as a way to constrain the nature of the dark matter particle, such as the mass scale of their free streaming and so on. But you can see that even for a fixed dark matter model, there's a lot of different aspects of the astrophysical process that can actually affect these abundances quite significantly. Yes?
Can you say a few words about patchy reionization and how it might play a role here or not?
Yeah, so patchy reionization certainly could play a role, because you could imagine, say, a Milky Way that lives in or a galaxy that lives in an overdensity. And if that region reionizes much earlier, then if you believe the kind of picture that I showed you before, you would think that that object would have fewer than the average complement of ultrafaints. These models here don't have a patchy reionization, it just sort of does it homogeneously. But certainly there can be an effect there. It depends on how big, I suppose, you expect the fluctuations to be in any given region. However, this, again, itself can't be the end of the story, right? Because if you look at a paper of a semielliptic model and you look at one of the tables that shows you all the parameters that are in there, and this is true for hydrodynamical simulations as well, this is kind of what it looks like, okay? There's a huge range of processes that occur in here. There's star formation, there's feedback, which I haven't really mentioned, there's reionization, there is how mergers occur or don't occur. And so it's really complicated sometimes to, I suppose, understand what is actually influencing the final prediction of a model, and is doing this sort of one-by-one test of changing one parameter or not enough to actually understand what is setting the predictive power of a particular model of galaxy formation. So a question that I've been interested in recently is, if you have a prediction of a model, say for a statistic y, it could be the abundance of galaxies, for instance, the abundance of these ultrafaints. For some predicted statistic y, do all of the parameters in a given model matter equally? Okay. How does the influence of these parameters affect not just the global prediction of that particular statistic, but how does it change from one bin to the next? Is it affecting the ultrafaints differently to the classical satellites, for instance? What are the interactions between these parameters? Are they completely independent, or is there some kind of nonlinear interaction that is occurring between them at second or third order or even higher orders? And finally, do these parameters in these models, which we think are representing physical processes, are they actually changing the predictions that we are making in a physically meaningful way? So how interpretable, I suppose, are these complex models of galaxy formation? Or stated differently, how sensitive are the properties of the dwarf galaxy population to physical parameters of a given model? So this is a particular question that we've looked at quite recently. And so to try and explore this is kind of the process we followed. So we first start by generating thousands and thousands of realizations of a Milky Way mass halo and its corresponding satellite galaxies through dark matter merger trees. And then we say that, okay, we have this galaxy formation model that has all of these parameters that represent physical processes like supernovae, and well, we don't think AGN really matters significantly here, but maybe how the star formation works, how reionization works. Let's vary all of these parameters and sample all the possible ways this parameter could be changed, these parameters could be changing in some higher dimensional space. And we do this through some kind of Latin hypercube sampling. And in particular, we decided to change around a few different parameters that we think will be especially important when it comes to understanding what sets the abundance of the faintest galaxies that we observe around the Milky Way. So one are the sets of parameters for reionization, so the time when it happens and this filtering scale that I mentioned. So it's a very simple prescription here. Another set of parameters which control now how effectively mass is ejected from galaxies in the form of supernovae. Exactly how that is represented, I'll show you in a second. And then some sets of parameters that determine the efficiency of star formation in disks, how easily starbursts are triggered in galaxy mergers, and so on. So in the context of this model, a galaxy is completely affected by the physics of reionization if it has a circular velocity or if its mass is below this filtering scale after the epoch of reionization. So it's just kind of an on and off switch. And supernova feedback in this model is treated as a sort of standard mass loading factor type effect, which basically says that you eject things out of galaxies more efficiently if they have shallower potential wells. That's what that circular velocity is parametrizing, and it has some power law dependence and some normalization. Okay. So you can go ahead and now make predictions of the luminosity functions over these thousands and thousands of different samples. And this looks like a mess, and it is, because it's basically saying that, well, you can predict anything you want, really, if you don't really care about what the parameters look like. So this is, again, what the data was from before. And in the gray, one of them is a reasonable model, I guess, but is a whole range of possibilities. But what I'm interested here is not really in understanding what is necessarily the best model, but rather what is making the model predict a particular shape or not. Okay. So to do this, a technique we use is something called sensitivity analysis. Okay, so the idea behind this is to bring some level of control in trying to understand where the variance in a model comes from. So say you have some kind of complicated model such that it makes some prediction y, the model is represented by f, and it has some set of parameters x, which is a d-dimensional vector. So you can then define what the variance of that statistic is with respect to the ith parameter by essentially looking at how the variance changes in this prediction when you hold everything else but that parameter constant and you vary it around. Okay. So the variance of y integrated in the ith dimension depends on obviously the distribution of the initial set of parameters and what the mean value of the expectation is when you integrate it over the entire parameter space but itself. And so by doing so, you can define something called a first order sensitivity index, which is represented by S sub I, which says that the first order sensitivity index of the ith parameter is this variance I divided by the variance of that statistic as a whole. And then for deterministic models, which is what makes this a particularly well-suited application to semi-analytic models, which tend to be more deterministic than a hydrodynamical simulation is, you can then actually normalize these in such a way that you can define not just the interaction or the contribution from a single parameter, but also the joint interaction between 2 parameters, 3 parameters, 4 parameters, and the total order of sensitivity. So now that we can do this, we can characterize or quantify sensitivities in this way. Let us now look at the luminosity function of Milky Way satellites again, but represented in the form of these sensitivities. And this is what it looks like. So this is again the brightness of the satellites on the x-axis. And now the quantities on the y-axis basically are the different quantities that go into the galaxy formation model. So reionization, star formation, supernova feedback parameters, and so on. And each of the pixels here is a bin in the luminosity function, which is colored by the sensitivity of that bin in the luminosity function to that particular parameter. Okay, so the more, I don't know what color this is, white or cream a pixel is, the less sensitive that bin is to the parameter, the more in the blue it is, the more sensitive that parameter is. And what you notice is that these two rows are where the sensitivity is highest. And these are basically the parameters that control the strength of supernova feedback. And it has an effect that is basically dominant across the entire mass range, which basically says that the first order dominant process in terms of predicting the abundances of these populations is set by the physics of the mass loading, or how effectively you eject gas out of the galaxies or not. And reionization, which is the first two rows on that scale, have a sort of second order intermediate effect. Okay. On the other hand, the physics that controls the efficiency of star formation, or indeed how easily disks undergo instabilities, or what kind of merger criterion you set in terms of starbursts and so on, have almost no impact on the ability to predict certain abundances for these galaxies whatsoever. You can now repeat this exercise for any statistic you want. And so another one I looked at is the metallicity of the galaxies. So this is now the mass metallicity relation, but now colored by these sensitivity indices. And you notice that the coloring is a little bit different from before, in that now even an even smaller set of parameters seems to show up as being important in predicting these statistics. In fact, again, it is the supernova feedback parameters that are the dominant effects. And reionization, for example, has almost no effect at all in terms of setting the final day metallicities of these galaxies. What about the higher order contributions? So is it just these parameters individually that matter, or are they coupling in some non-standard way in making these predictions? You can do this by measuring something called the total sensitivity index, which I'll explain in a second. So this diagram is the same as the one that I showed you before, but now I'm just showing the actual values rather than coloring them in pixels. So these are the first order sensitivity indices. And now the solid lines are showing what the total sensitivity is of that parameter, which encapsulates both its contribution and its contribution after interactions with all other parameters in the model. And if there's a big gap between the solid line of a color and the symbols of that same color, it means that that parameter shows lots of higher order interactions. So you notice here that this is for the luminosity function now. Again, it is this parameter there, which is the power law that goes into the mass loading factor, if you care about that. That is still dominant, but there's a big gap between its first order sensitivity and its total sensitivity, meaning that it's not supernova feedback alone that is influencing these statistics. So the demographics of these populations but it's coupling quite strongly with some of the other parameters in the model. If you contrast this now with what's happening with the metallicities of these galaxies, you find, again, a similar picture to before, but now the gap between the total sensitivity of the model and the first order sensitivity of the model is much lower, meaning that at least in the context of the model that we are studying, the metallicities at first order are being set by the physics of the supernova outflows. So you might ask, why have I chosen these two statistics in particular? Okay, so the number counts of these objects and their metallicities. It turns out that there's kind of an interesting tension that exists between them, which can be sort of shown in this way. So here is now the number of satellites as a function of their brightness, and now the metallicity of satellites as a function of their brightness. You can take your galaxy formation model and tune it in such a way that it is fit specifically to these data. And when you do that, you get something that completely undershoots the metallicities, because essentially in order to bring the vast number of dark matter halos into agreement with the relatively few satellites that we observe, you need really strong suppression to the star formation, and that's blowing out all the metals. If you do the reverse process, where you fit it to these data, but try to see what it predicts for the other, you get something that completely overpredicts the presence of certain massive galaxies. Okay, so these two different data sets are actually kind of pulling you in opposite directions. And you can kind of understand this through another kind of statistic that we explored in this, which is called Shapley additive explanations, which basically tells you how much a parameter is contributing to the direction in which the prediction is made, not just whether it's making an effect or not, but also the directionality of the change. So in this diagram, what I'm basically showing is a particular bin, okay, focusing in the ultrafaint regime for the luminosity function and the mass metallicity relation. And the color shows you whether that parameter is increasing or decreasing, if I increase the value of the parameter or not. And this basically shows the direction which it pushes the statistic, either increases the number counts or decreases the number counts, increases the metallicities or decreases the metallicities. And the main thing you want to take away is that the direction in which the colors go are basically inverted between the two data sets, in that the mass metallicity relation wants weaker feedback, essentially, and the luminosity function wants stronger feedback. So this is actually the kind of test that you can do very robustly with certain types of galaxy formation models that could be really instructive in trying to understand how to break degeneracies between astrophysical parameters by looking at data sets that are actually trying to pull the parameter space in opposite directions. As an interesting aside, one of the things, and I won't talk about this point for too long, one of the interesting outcomes of this that we found is that if you now look at predictions for the sizes of galaxies, okay, the half-light radii of galaxies as a function of their brightness, then models that are kind of fit in such a way that they do a better job of reproducing the metallicities of the galaxies tend to also predict sizes that are in better agreement, okay, for free, without including that as a separate context. So these are basically what happens for the size luminosity predictions for these galaxies in the fiducial case, or when you fit just the luminosity functions. But when you condition them on fitting the mass metallicity relation, you get something that automatically shifts to getting sizes that are in better agreement as well. And this final model was a slightly contrived case that was able to fit both of these data sets jointly, which basically suggests that whatever is setting the physics of the metallicities is also very deeply connected with what sets the final day outcomes for the sizes of these galaxies, at least in the framework of this model.
Does that include stripping?
Sorry, this is stripping for the sizes. Not a huge amount. So that's one of the reasons why we don't get the really compact objects, but the effect of the stripping for relatively brighter objects is pretty small, which we've checked in a separate exercise. Okay. All right. So I want to now shift to smaller scales than this, where we go to the case where there are no galaxies to worry about. And this is now focusing in the regime of objects between, say, a few hundreds of solar masses to a million solar masses or so. So this is a regime that's kind of difficult to simulate, but we have some very specialized sets of zoom calculations that I'll talk about in a second that allows us to resolve this. So this is work that was done by a former student of mine who's now a postdoc in China to try and see, do we expect lower mass halos, so things that are below, say, 10 to the 6 solar masses, to actually contain baryons in them or not? So these images basically show the examples of 3 different types of calculations. One which has been run with just dark matter, one in which there's dark matter and some non-radiative gas, and one in which there's dark matter, gas that is able to cool, and now you also introduce an ionizing background. And so the images basically show cutouts of the predictions of these simulations, with the total matter shown at the top, only the dark matter shown in the middle, and the baryon distribution shown at the bottom. And the main thing to notice is that, firstly, the total matter, which is the gas and the dark matter, is very similar to the dark matter only distribution. Okay, so the dark matter is fundamentally what is driving the shape. But if you look at this bottom panel here, you notice that if you zoom into a little region like a filament, in the simulation where there is non-radiative baryons present, the gas actually follows a distribution which is very similar to the dark matter distribution. So the gas traces the dark matter in the filament. But as soon as you introduce an ionizing background, the ionizing background unbinds all of this gas, and basically the whole region becomes diffuse. Okay? So this is because the entropy becomes too large. So much so that if you actually look at the large-scale projection of the gas distribution in a simulation where there is non-radiative baryons, it looks almost identical to what the dark matter distribution does. But when you introduce this ionizing background, it basically completely streams out of this region. Okay. So the question is, what does this actually do to the dark matter halos themselves? It turns out that this evacuation of baryons due to the reionization effect has an effect also on how quickly dark matter halos are growing. So in this diagram, we're focusing on a particular mass scale of objects that have a final day mass of around 10 to the 6 to 10 to the 7 solar masses or so. And it's showing, as a function of redshift, the growth of the mass of the halo. Okay. And reionization in this model is occurring where this vertical dashed dotted line is. And prior to reionization, you see that the 3 lines, so the dark matter only, the one with the non-radiative baryons, and the one with reionization, all agree perfectly. But as soon as reionization kicks in, the simulation with the non-radiative baryons basically continues following what's happening in the dark matter only case, whereas the one in which there's reionization, the halos there are growing more slowly. Okay. And why this is essentially because by removing the baryons from the potential wells of the dark matter through reionization, you've basically made a shallower potential well, because in the other cases you had dark matter there or baryons there that allowed them to continue growing faster. But you've now removed that source and basically slowed down the growth rate of the halo. And this has also an effect on the density profiles of these objects, where if you now look at what is the total matter distribution measured from the center of the dark matter halo to their exterior, you notice that in the case where there were once baryons that have now been evacuated through the presence of an ionizing background, the central densities actually also drop by about 40% or so. Okay, and this obviously has an effect on what we think will be the ultimate contribution of this mass scale of halos to something like the annihilation luminosity, if dark matter is indeed annihilating. And that's a topic that I will touch on in a second. So finally, you can actually see what is the fraction of baryons these objects actually contain as a function of time. Okay, so this diagram basically shows as a function of dark matter halo mass on the x-axis, the fraction of baryons that they contain normalized to the cosmic average. And what you see is that at early times, okay, this is prior to reionization, there's actually two different curves here, but they're just on top of one another. The non-radiative case and the simulation with reionization are identical. But once you introduce the ionizing background, you'll see that as time progresses, the baryon fractions decrease quite drastically. So much so that basically below a mass scale of around 300 solar masses or thereabouts, you can essentially say that these dark matter halos have never seen a baryon in their lives. Okay? So this basically tells you that in terms of the visible content of dark matter halos, there is a particular mass scale below which you don't expect them to contain any baryons at all. Okay, so how do you actually then even hope to see the tiniest dark matter halos if they don't contain any stars, they don't even contain any gas in them? And it turns out that the way you can do this is by trying to see whether they will shine in their annihilation luminosity or not. And this brings me on to what is the final section of my topic, which is going down to the very, very smallest scales of structure formation, to the very limit of where dark matter halos even possibly form in a cold dark matter universe. So this spans everything from 1,000 solar masses down to 10 to the -6 solar masses, so corresponding to the mass of the Earth. Okay. So what are the properties of these objects? This is kind of an uncharted regime. Okay, this is a regime that we don't often think about when it comes to MRD simulations. If there's something that we know about dark matter simulations historically, that is that there's three certainties, right? Death, taxes, and NFW profiles. Okay. And the idea here is that no matter what mass scale you look at, whether you're looking at rich clusters, Milky Way mass objects, or dwarf galaxies, if you rescale the density profiles of dark matter halos by some convenient units, irrespective of what mass scale you're looking at, they basically collapse to this almost universal shape, which we call the NFW profile, which has three slopes: a central slope that goes as r to the -1, a profile that in the middle goes as r to the -2, and something that drops as r to the -3 in the outskirts, okay? But you can ask this question, well, people have established this very well in simulations down to say 10 to 6, 10 to 7 solar masses or so, but if indeed structure formation goes on for another 12 orders of magnitude below this, is this true even on those scales? Because what shape these have actually matters for what we think dark matter will do in terms of annihilation. So this is actually quite a hard problem, so much so that when people have done the appropriate simulations to resolve structures of those scales, you have to do this in a very specialized setting. So this is some work that was done by Raul Angulo and collaborators a few years ago now, where you start with a very tiny box. So it's 20 kiloparsecs or so in size. And this tiny box allows you to resolve really, really tiny objects, okay, which are the ones that we're after. But by virtue of these being very small boxes, you have to stop the simulation at very early times, okay? And that's primarily because the nonlinear scale becomes comparable to the size of the box. The whole box should be collapsing, but that's not happening. So you have to stop these at very early times. And when you do that, you can then extract these objects, these Earth mass halos, and measure what their profiles look like. And they look something like this. So this is density as a function of radius for 6 different objects. And the color coding is a color coding on the redshift, okay? As you can see, the lowest redshift they get to is about 30. And what we notice is that this doesn't really look like NFW at all, okay? These are single power laws with slopes of around -1.5. So in other words, if this is true, then this almost universal tenet that we have, that things follow this universal structure, is no longer accurate, that NFW profiles don't actually exist on these small scales. But is this picture also true if we were able to do this calculation all the way to the present day? Okay, because we've stopped this at some special time. Is this actually true if we push them all the way down to the present day? So like I said, this is a very hard calculation to do. So how do you actually get around doing it? So the way we do this is through a technique called the zoom technique, which is where you start with a very large volume. Okay, this is a volume that is around 740 megaparsecs in size. This is basically the Millennium simulation, but just run with Planck cosmological parameters. So the characteristic mass scale is around 10 to the 14 solar masses here. What you then do is you pick a region of interest, you keep the rest of the volume the same, just degrade its resolution, and you focus your computational power in that center. And that then allows you to resolve a smaller region at higher resolution. So now in this next layer, the characteristic mass has gone down by a factor of 100. So you can then pick another region, repeat the process, pick another region, repeat the process, repeat the process, repeat the process, repeat the process, repeat the process. We're almost there. Repeat the process, okay? 8 or 9 times over, such that now the characteristic mass scale is 10 to the minus 6 solar masses. These are Earth mass halos, still embedded in a 740 megaparsec cosmological volume. And now this is a calculation that can be done down to redshift 0 because you have all the large scale structure. To put numbers to what this looks like, by the time I said repeat the process twice, we got to a case where the mass resolution was about 1,000 solar masses. This is what people call high resolution simulations. By the time we get to, and it is justifiably so, by the time we get to the highest level, an individual particle has a mass of 10 to the minus 11 solar masses, okay, embedded in a cosmologically representative environment. So this is a project that eventually led to the creation of the Gadget 4 code, actually, because we had to develop a lot of new algorithms to do this. So now that you can resolve all of these structures, you can actually put things together and make the definitive mass function of dark matter halos. So it's just number of dark matter halos as a function of their mass. Okay, so the first 3 levels basically allows you to span everything from the sub-dwarf scale up to the clusters. And when you put all of these levels together, you span an impressive 22 orders of magnitude in halo mass, okay? And they all seemingly fall on a fairly well-defined power law slope. Okay. But what about this question of the profiles? So this is now at redshift 0, the density profile of the dark matter halos, so the density as a function of radius, they all sort of have been rescaled in a certain way that allows you to put them all on the same graph, essentially. And they all follow kind of a very similar behavior, and they seem to be very well defined by an NFW profile. Okay, in fact, it's a slightly different version of NFW. Well, it's a different version of things called the ionosphere profile. Okay, so this then is a quandary because this says that there's a tension now between what people are finding in those high redshift simulations and what we are seemingly predicting when we go to that same mass scale, but down to redshift 0. So there's some contradiction between what is happening in terms of the final day assembly and what happened during the initial collapse of the halo. So to try and understand this, you can ask the question, well, what does theory expect or tell us to expect in terms of collapse? So there are various different models that people have come up with when it comes to the collapse of mass shells as a function of time. The idea being that you have some kind of scale invariant self-similar infall of mass shells that build up as a structure decouples from expansion, and doing so allows you to write down a system of equations that allows you to predict what the scaling of the density should be as a function of radius. So this is all of these idea of self-similar collapse and secondary infall and so on. However, in the case of the formation of the initial peaks themselves, so things are forming really at the cutoff scale, these 10 to minus 6 objects in cold dark matter, they don't really follow the self-similar behavior in the traditional sense. In fact, the structure formation is really quite manifestly different. They formed almost instantaneously as the peak is formed, and they're really sharp features that are called prompt cusps. Okay, so they're prompt because the peak collapses almost immediately. And using analytic arguments that are kind of similar to what you get from self-similar collapse, you can find that theory should tell us to expect that the density should vary with radius with a power of -12/7, which is kind of like -1.5 that we saw in the simulations before. Not quite, but it's close to that. So how is this thing then eventually changing towards the NFW form that we see later on? So this is something that my student Yuchan Wang has been looking at. So what it requires you to do is to study the formation of dark matter halos really at the scale below which there are no more fluctuations, so that you have pristine primordial peaks that are collapsing, whose evolution you then follow thereon. And you can either do simulations that are really, really high resolution on the scale of these Earth mass halos for CDM, or you could just do a toy example where you just truncate the power spectrum artificially yourself and say that we're simulating like a dwarf galaxy, but in a case that looks kind of like warm dark matter, perhaps. So this is kind of the setup of the calculations that she's done, where basically you have a bunch of initial power spectra that have been cut off on some particular scale. So this corresponds to the sort of wave number at which the power is suppressed. So where the value is really high, that means you allow the power spectrum to extend to smaller scales. Where it's low in wave number, that means you've suppressed more and more power, okay? And the vertical dashed curves basically show the typical, the characteristic wave numbers where the halo itself is forming, okay, given by that. So to give you an example of what truncating the power spectrum like this actually does to the evolution of the halo, you can look at this example here. So this is the case of the same dark matter halo that has now been involved under 3 different conditions where the power spectrum has been cut off on relatively large scales or on very small scales, okay? And if you run this forward, you see something like this. Okay, this is the same object, but just slightly changing the level of fluctuations in the initial conditions. In the case where you allow lots of small scale power to exist, you see lots of mergers, you see smaller objects that collapse and join with the initial peak. In the case where you cut off power on relatively large scales, there are no small scale structures. So all you're seeing is just basically the collapse of the primordial peak itself.
What are all the little dots? Is that from fragmentation?
Yes, those are numerical fragments, yes, which I spent too much of my life thinking about those things, but I'm very happy to talk about that later on. But yeah, those are artificial fragments. So you can then ask the question of where does the mass in a dark matter halo actually come from, okay? So this is now those same videos that I was showing you before. So the same object that has been simulated with a cutoff imposed on smaller and smaller scales. And now we take the particles that belong to their density profile at the end and trace them back to the initial conditions. Okay, so this is where the x-axis basically tells you the distance of particle from the initial peak that collapsed, and the y value basically tells you of the linear density of the particle in the initial conditions. And you can see that, where the material comes from in a simulation where there's lots of small scale power is really messy compared to one where there is an absence of small scale power, which kind of makes sense, okay? So clearly these distinctions will have an effect on what the final day profile looks like. So in other words, why does something that initially collapses at peak first look like a power law profile, but eventually transition towards an NFW-like form? You can actually use these simulations to see this process taking place step by step. So here is now the same object at 3 different times, okay? So these are the distribution of the particles at 3 different times, the distribution in the initial conditions. And the column on the right is now showing the density profile. So density is a function of radius, but now density has been multiplied by r to the 12/7, so that if the density profile looks like this prompt cusp-like solution, it should be flat in that curve. Okay? And the red curve basically shows the particles that were associated with that initial pristine peak itself, the prompt cusp. And the white shows the total density profile, which is then a sum total of everything else that has merged onto that object beyond the peak itself. And you see that at early times, things are flat, okay? Meaning that actually they are following the prompt cusp-like solution. But as you go to later and later times, the particles that were associated with the initial peak, the pristine peak itself, remain sort of flat, but it's the exterior part of the profile on larger scales that is actually changing. It is the accumulation or the aggregation of mass coming from beyond the initial density peak itself that is actually building the shape of the profile going out to larger scales, okay? So this initial prompt cusp type solution, this thing that looks nothing like NFW, is still present, but buried deep in the center of the dark matter halo. But the shape or the overall NFW-like shape that comes through is therefore being built on top of this through the accumulation of further and further material. And so here's an example of how this actually builds up in the case of a merger. You see that as time progresses, you can separate out the particles that are part of the initial peak itself in the solid and the total density profile, which are the dotted lines. And the NFW shape in these units basically looks like this. And you see that the prompt cusp always follows this sort of flat distribution, and the NFW actually is what is built on top of this through the aggregation of other material. So if you were to make a picture of how the NFW is actually then created, it's basically as follows, which is that you start off with something where the true density profile is an NFW. There is a prompt cusp with this yellow, but then through mergers with other halos, interactions with other objects, or indeed the aggregation of artificial filaments, everything seems to universally transition towards the NFW-like form with the prompt cusp in the center. And why does this happen pretty generically? I think the answer to this has been known for a long time. It's simply that dark matter halos themselves have a very well-defined self-similar accretion history, which is itself, when rescaled in particular units, of a shape that looks like the NFW. So this is something that Aaron Ludlow and I did a few years ago, where you take halos of all different masses, you find out what their accretion history is, you can scale them by some units, and when you put them on a graph, which puts their accretion history and the density profiles in these rescaled units, you find that the density profile and the mass profile are of identical shapes. And so what this basically shows is that there's little dependence also on the nature of the cosmology, the nature of the power spectrum, and this is indeed a very universal prediction. So I think what this basically suggests is that the reason why we get universal profiles is simply that dark matter halos have universal accretion histories, which is itself, I think, going to be a product of something like Gaussian random fields as the initial conditions. And all of this matters in the form of dark matter annihilation, which I don't know if I'll have the time to talk about that now, but I'm very happy to talk to you about separately. But so in that spirit, let me just finish off with what my concluding thoughts are. So we talked about 3 different scales. We talked about the edge of galaxy formation, which are the regions where galaxies are fundamentally affected by processes in the early universe, such as the Epoch of Reionisation. And semiotic models have been really helpful in understanding how these different processes are shaping the galaxy population and how many different things can conspire in addition to the nature of the dark matter to giving you a population that we actually observe around the Milky Way today. When we go down to lower mass scales than this, you get to the regime where no stars will form, but there's only a limited range where baryons are ever able to assemble. And this, I think, turns out to be a particularly ideal regime for tests of dark matter, because this is also a sort of mass scale where models of dark matter tend to be at their most discrepant. And the effect of an ionizing background is such that there is a particular mass scale below which halos will almost never have seen a baryon in their lives, where the baryon fraction drops down to essentially 0. And finally, even smaller dark matter halos, even though they can't be observed due to their stellar content or their baryonic content, they can be observed through their contribution to the annihilation luminosity. And one of the things that we've come to learn is that this universality of halo profiles actually is universal in two senses, in that everything generically has this prompt cusp formation when the initial peak collapses, but almost very consistently converges towards this NFW-like forms. And exactly what the shape of these central density profiles is can make vastly different predictions for how much we expect to see the contribution of these low mass substructures to the annihilation luminosity in the Milky Way, which I think is one of the best ways to actually test this hypothesis of the prompt cusp halo formation. So that's where I'll stop. Thank you.
Sownak. Let's take a few questions.
Hi, thank you for a great talk. I was wondering, for this transition from the prompt cusp to the NFW, is there like a generic convergence redshift, or is that convergence redshift going to depend on the mass of the system?
I think it will have a mass dependence at some level, because the closer you are to the free streaming scale, you will have fewer interactions with other mergers. And so as soon as these initial mergers take place, they're very effective at building up this outer profile. So there will be a sort of time and mass scale dependence.
Raj?
Thank you for the great talk. I really like the sensitivity analysis and trying to jointly fit the luminosity function of ultrafaints, the mass metallicity relation, and the size mass relation. You showed that you were able to find a combination of your parameters that fit both the sizes and the metallicities. Did that combination also reproduce the luminosity function?
Right. So the combination that fits the sizes was never used to fit the sizes. That came out as a free outcome of the model. The model that there was a model that fit the luminosity function and the metallicity separately, and then one that fits them jointly. And that also happens to give you sizes that are in good agreement, which is, I think, what is interesting about this, that you don't include the sizes at all in this calculation, but somehow the physics of what sets the feedback parameters for the metallicities is actually also giving you something that gives you consistent sizes.
Yeah.
Yes. So how does your beautiful evolutionary scheme fit in with these observations, such as in the relics survey or Cloud9, where these objects which seem to be starless but gas-free? In your picture, you don't really make a distinction between gas and stars, but do you predict a regime where you might have only gas but no stars?
Yeah, so I mean, the relics is actually, oh God. The picture that I showed of halos crossing this critical threshold for star formation and so on, one of the natural predictions of this is these reionization limited H1 clouds, these relics. So you do get a particular mass scale where they can trap baryons. Okay, so these would be of the order of 10 to the 9-ish in halo mass. So they're large enough to have cooled baryons in them, but not form stars in them at all. So they would be a natural prediction of this model.
So you'd say, and the observed scale is consistent with your predictions? I mean, we know the numbers, there's numbers and mass scales, so they are consistent with your picture?
Yes, actually. So what?
Nice.
So there is one of these things that's being led by Alejandro Benitez Lampe, which is basically looking at exactly doing a census of these kinds of objects and the sort of scales that they infer as to where this lies in the observational data is sort of consistent with this picture of the hydrogen based thing.
try using this. Thanks for the great talk. I wanted to go back to the sensitivity analysis. And I was interested in knowing whether it makes sense to try and apply this analysis to different satellite systems, like M31 is a case that comes to mind, or I think like the LMC is also reported to have satellites. Yes, I'm wondering if that has been done at all, or if that's something you're thinking about.
Yeah, so I mean, I should stress that the sensitivity analysis is agnostic to the system you're applying them to, because it is basically telling you how sensitive are the predictions of your galaxy formation model to a statistic. Of course, then, yes, you could then say, okay, now let me make predictions for the abundance of satellites of an M31-like system. So you can say for a slightly different halo mass, or for even like 10 to the 11 solar mass systems like LMC mass hosts and stuff like that. But that is very easily generalizable.
Thank you. I enjoyed the breadth. As halos, before halos become larger than having a virial temperature larger than 10 to the 4 degrees, they go through a stage where they can form molecular hydrogen, cool, form stars, explode, impact the rest of their evolution. So you didn't touch on that cooling mode in your talk. Do you want to speculate a little bit about how that would impact your results?
Yeah, so the molecular hydrogen cooling is, I think, one of those things where I don't know if there's really a consensus on what the level of the contribution is to these objects. From the tests that I have done, which involve a molecular hydrogen cooling channel, they produce, so what it does is that it changes the lowest mass halos that actually form stars. If you think of it in terms of the occupation fraction of halos, or fraction of halos that are occupied by galaxies, that does shift quite significantly. So in fact, in this case of hydrogen cooling only, basically about 50% of halos with masses of 10 to the 9 or so are empty. When you introduce molecular hydrogen cooling, that shifts to something like 10 to the 7, maybe a few times 10 to the 6 even. So that has a significant effect. But the amount of stellar mass that is formed through that molecular hydrogen cooling channel is few hundreds of solar masses. So I think in terms of the overall contribution to the final day masses of the ultraphanes before the Lyman-Werner background will then destroy the molecules, or the next generation of star formation kicks in, seems limited, at least in the context of the models that I've been experimenting with.
Right, just a quick follow-up. I mean, they form POP3 stars, so actually it contributes by redshift zeros, probably almost no mass quantum contribution, but it does impact, it provides metals, it impacts the entropy of the halos in which they form, and therefore the rest of the evolution. Exactly,
yeah. So there's a project of very high resolution simulations of dwarf galaxies that we're doing called Lyra, which basically incorporates all of these effects. And indeed, there are some differences, quite significant differences that are made with respect to these models that have only these sort of atomic hydrogen cooling channels because of all of these added effects. So in terms of like individual stochastic behaviors, I think you can get a huge number of variations to the very general picture that's presented here.
One last question.
Not a physics question, but were the beats on a string instability, those halos, have you looked at the density profile for those to learn anything?
Yes, so the profiles of the beats on the string things themselves. We work very hard to get rid of them. So they have very curious distributions in their shape, actually. Actually, one of the methods that we use to identify and get rid of them is by actually tracking so let me just to bring everyone up to speed about what I'm talking about here. It's essentially, this is going to go very slowly, isn't it? essentially in any simulation of structure formation that you run where you have a resolved cutoff, you will get fragmentation and nonlinear collapse on scales that are below the scales where gravitational perturbation should exist, which are these little tiny lumps, and they are very uniformly spaced along the filaments, and they're called these beads on a string. So the way they're actually identified is based on the difference in their structural distribution compared to the real halos, because actually if you trace back the particles associated with the dark matter halo to their Lagrangian conditions, they look like these amoeba shapes. But for these things here, when you trace them back, they actually look like little pillboxes. They're kind of these extended cylindrical shaped objects. That's actually one of the criteria we use to get rid of them. In terms of their density profiles themselves, I don't have a particularly good memory of exactly what they look like. But I would imagine that there would be some kind of some difference there.